Hello, everyone, and welcome to the AI on Demand webinar series, AI Innovation from Research to Markets. So my name is Loredana Bucșeneanu. I am a project manager at the European Digital SME Alliance, and I'm also a member of the AI on Demand team, and happy to be your host for today's session. For those of you who are not familiar with AI on Demand, it is a community-driven platform designed to empower European AI research and innovation ecosystem by providing a series of resources such as data and AI experimentation tools, AI assets and data, and also information about trainings and learning resources, but also information about events and funding opportunities. So as part of the objectives of the AI on Demand platform, this webinar series aims to showcase AI innovations developed in the research environment that demonstrate the real-world application. So the series brings together research and industry and tries to highlight AI tools and services that support the business ecosystem and developers in advancing their AI-driven solutions. So throughout today's session, we will explore how AI and robotics are being put into practice, from automating routine and repetitive tasks to streaming logistics, supporting smarter decision-making, and empowering human workers rather than replacing them. So you'll hear practical demonstrations and expert insights that show not only the benefits, but also the key considerations when it comes to integrating these technologies. So I'm very happy to present the experts that will guide us through today's discussion, namely Miguel Seriani, researcher at the Institute for Cognitive Sciences and Technologies, part of the National Research Council of Italy. He's joining us on behalf of the HACID project. We also have Maria Chiara Leva. She's co-chair of the Master in EHS at TU Dublin and co-chair of the Technical Committee for Human Factors in the European Safety and Reliability Association. And she's also coordinator of the Marie Curie project, CISC, on collaborative intelligence for safety critical systems. And together with Chiara, we also have Ayush Jain. He is a postdoctoral researcher at Atlantic Technology University, and also Doa Almatawi, researcher at Matema. So I suggest we start the presentations with Miguel. So I'll give the floor first to Miguel, who will talk about the hybrid human-artificial collective intelligence in open-ended domains as part of the HACID project research. So Miguel, you have the floor.
Thank you, Loredana, for the presentation. Sorry for just a moment for the setup. I think now everything should be okay. You should be able to see my slides. My plan for this short presentation is to give you a brief idea of what this project HACID is about, and about the specific work we've done and resource we created in the context of this European project. So as you can see from the first slide, I put some names. Obviously, it's not. It's just a part of the people involved in the old project, but these are the people that were more involved in the creation of this specific part. That is this knowledge graph for climate services. And these people is mostly from the Institute for Science and Technology of Cognition of the National Research Council of Italy and the Met Office from the UK. So, okay, to start with, what is this HACID? So this hybrid human-artificial collective intelligence in open-ended domains. What we mean by that? Let's start from the last bit, open-ended domains. So we're talking about, in general, any kind of complex situation in which you're looking for solutions that are just not just a simple classification. And obviously it can encompass many possible use cases, but the use cases that are specifically in the project are about medical diagnostics, the first, and the second one about climate services. That means basically how to help to adapt to the challenges related to climate change and the risks related to climate change. We know there are a lot of things we can do, obviously, to try to mitigate climate change or to avoid the worst possible outcomes. But we know that a lot of things are going to in a lot of aspects the climate is going to change anyway, and we're going to have many extreme events, and we need to adapt to that. We need to prepare to that, basically. So what's the collective intelligence part? Collective intelligence, the idea is pretty basic in some way, is that getting ideas and solutions for multiple people, you can get better results, in a way, to say it very simply. And in order to do that, you need to offer some way to aggregate these multiple solutions, multiple ideas. So, and there are many aggregation algorithms that try to do that. And so we are applying this aggregation algorithm. And the other aspect is that this hybrid human artificial intelligence, it means we are not just basically collecting solutions from experts, but what we do is also see how artificial intelligence agents can help in this process. So it's not just the artificial intelligence agent giving the solution, but the artificial intelligence agents giving solutions that, together with the solutions, ideas, contribution by human experts, may improve the collective solution. So I'm going more towards what I'm presenting specifically now, that is a data asset, to say, so it's a knowledge base. So how to support this kind of platform? So we need to have some core data asset that we are using, what we call a knowledge graph. Some of you may know what it is. I may tell you something more about that, but let's say it's a kind of a database, but more flexible and designed for interoperability among different data sets and different sources. And we have this knowledge graph that you use as a way to have a common understanding of a domain by these multiple agents interacting with the system, and a way to exchange information. So going more to the specifics and talking specifically about the climate service case, but this works also for the other use case, actually. What we have is not just, let's say, a monolithic knowledge base, but a knowledge base that is composite. And there's a part we call domain knowledge, that obviously is the knowledge that is known and common about that domain. And there is the knowledge that is specific of a single case that is managed by the system. The interesting thing is that these aspects and these different kinds of information interact, and having this kind of composite knowledge graph gives us the opportunity to have this, let's say, layered approach, in which we have these links between the specific cases and the domain knowledge. So regarding the specific case of climate services, I'm going forward still very high level, then you can ask me more technical details. I avoided to put the technical details almost at all in these slides. So what kind of things we have in this knowledge graph? We have these nodes that are different kind of concepts, and the kind of concepts, the typical, say, kind of concepts we have in the domain knowledge about climate service and that we represent are about climate models used to predict or to project how the weather will be. So what does it mean? That these climate models are basically some set of rules based on physical laws that determine how a system evolves. And then a simulation is an execution of a climate model using considering some constraint. Specifically, one of the most important constraints is deciding some emission scenario, so some evolution that the world we have in terms of emissions in the next decades. We are talking about simulations that go forward for decades and sometimes hundreds of years, maybe 100, 200 of years in the future. At the very least, like 50 years in the future. And then this simulation produces an output that is a data set. So a data set in which we have basically as data points these like the values, for example, of temperature or pressure in different places of a grid that may be of the whole world or of a specific region, and in time we may have values for each day or each year. So we have a lot of different cases. So this is a very simple view. Then we have more information we want to represent. For example, in relation to the climate model, we want to know who is the organization that maintains a model. Then a model has some features. For example, it supports some physical laws. It has some approximations that we want to describe. Then when we use a model to do a simulation, there are other parameters that we can change. So we actually, the climate expert, the climate organization that runs those models. So we also have to represent different configurations for the same model that obviously have effects on the results of the simulation. Then for a data set, in the data set, we have multiple variables that are represented. So for example, temperature, pressure, amount of rain, etc., and more complex derived variables. And then we got other characteristics, properties of a data set, like the spatial coverage, the spatial resolution, temporal coverage, temporal resolution. And then these data sets that are produced in the simulation, these are not just single tables, but are a composition of multiple tables, because we may have, for example, data represented in multiple granularities or split among different temporal coverage. So we have data sets that are composed of multiple sub data sets. So this is in a way, it's very simple in respect to the real structure that there is in the knowledge graph, but this is to give you an idea of what is that we are representing. This is all we represent the information about actual climate models, simulations that have been run in a number of experiments. We don't store in our knowledge base the actual data points, so like the temperature at a certain point, because it's not the purpose of the project. We would not have such capacity for such a number of different simulations. It would be really hard to represent all that data, but what we represent, you can consider it to be the metadata that allows an expert to then find where is the interest, where are the interesting data sets that he have to use that then to do other transformation. There are other aspects also are represented in in the knowledge graph. I don't have time to show you all in detail. So what are the steps or the ingredients that we use to create this knowledge graph? First of all, we use the semantic technology stack that maybe some of you may be familiar with. Is the technologies and standards developed for the semantic web, linked data, so RDF, OWL, Sparkle, but I can give you some basic information about that later if you want to know something. The other very important thing is that we are not just I consider myself a knowledge engineer, but I'm not. It's not that I decided myself what I have to represent in this knowledge graph. So we worked together with climate experts, especially from the Met Office, that is the most important organization for meteorology. Yes, sir, the governmental meteorological agency in the UK. And with their climate experts, we co-designed this knowledge graph and the data model. Talking about the data model, we designed this common data model and published using semantic standards, so as an ontology. Then we map existing data sources to the model using declarative ways, standard ways. We published that online, so it is available online with open license, and it's still we are still developing it and improving it, adding more data sources. Just thought now the numbers are not that huge, but we represent the data about like 150K data sets, 2000 simulations. The models are less than 100, and these variables are quite different climate variables. There are 700, and that's a total number of triples. That is a way to measure the size of knowledge graph is around 3 million. Okay. With this, I ended, and these are some links to the things are presented, and my email, contact email. Thank you.
Thank you so much, Miguel. I will also maybe we can post the link in the chat if anyone wants to have a look at it. And then if you have any questions for Miguel, we can definitely address them at the end of the presentations. I suggest we then move to another case, so we can look into the results of the CISC project. And I would like to invite Ayush to tell us a bit more about what they have been working on.
Yeah, okay. Cool. Thank you, Loredana. Thank you for the opportunity. So today I'll talk about advancing the understanding of human in the loop, AI enhanced application in safety critical context. These are the interim findings from two of the research efforts. The first one is CISC project, and the second is RoboMate. Both these projects basically address how AI and collaborative intelligence can effectively integrate into safety critical systems. And last but not least, I would like to thank the Adapt Center, the SFI Science Foundation Ireland, and EU for funding these projects. So let's get into it. So CISC basically stands for Collaborative Intelligence for Safety Critical Systems. So it's a Marie Curie innovative training network where our aim is to explore how human and AI collaboration can improve safety, resilience, and performance in domains like manufacturing, control rooms, and robotics. So this is truly a collaborative effort across industry and academia. We are 14 PhDs, and I think more than half of us have graduated already, and next half, or some will be graduating soon in coming months. And our network spans into multiple countries, which include major industrial partners like Iveco and Matema from Italy, Pills from Ireland, Yokogawa from UK, and Digital SME from Belgium. Plus, also it includes innovative academic groups from TU Dublin and Politecnico di Torino. So yeah, let's get into what automation and versus collaboration is. So the process of automation in the industry with the implementation of robots in the workplace had a huge impact in the productivity of companies and growth of the economy of these countries. However, as Dougherty and Wilson said back in 2018, that automation alone misses the mark. The future lies in collaborative intelligence, where machines augment humans' capabilities rather than replacing humans. So CISC builds on this philosophy by focusing on human in the loop systems in safety critical contexts. Now we studied more deep into what these human in the loop configurations for collaborative safety critical intelligence applications are. So this visual basically highlights different domains where human in the loop systems are essential. Our work basically centers on the red highlighted domains, which includes industrial robotics, visual inspection, and alarm handling, where we have conducted experiments, extensive experiments, which we are going to talk about in the coming slides. And we emphasize more on designing systems that support human understanding, decision making, and human well being. Uh, the whole CISC project basically includes three living labs, where each of the living lab is focusing on real world application. So, first live lab, which is human robot collaboration. It includes IMR, which is Irish Manufacturing Research, then PILS and Think. The second live lab is based on augmenting human performance in manufacturing. And the third live lab is centered around human decision support in control room environments. And each live lab is basically co-designed with end users in mind to reflect the practical and operational challenges. So I'm going to go through now what the first live lab is. So in the first live lab is titled Telerobotic and Human System Interaction and Interface, where we studied human system interaction during teleoperation and a cutting task. So we evaluated and conducted extensive user studies, and we evaluated task performance based on cut qualities, time, collisions while teleoperating the robot. Then operator, we also tracked operator state through EEG. If you see this, there is an EEG cap on the human. You can see. Then eye tracking and multiple questionnaires. And we also took the interaction data where we checked the system usability and the response. So the key goal behind this live lab was to design an interface that enhances user performance and reduces mental workload. Now, coming to the second part of Live Lab 1, which is naturalistic learning for cobots. So this work basically explored mutual expectations in cobotic systems. What does that mean? That what the robot expects from the human and what the human expects as a feedback from the robot. So that's what we were basically trying to understand in this kind of live lab. So we designed interfaces and evaluated different physiological measures like pupillometry and subjective ratings. This helped us tune a robot behavior to real human responses. And the result of this was a RoboMate project, which is a separate project, but a continuation of a continuation of this Live Lab 1B, which is to design accessible, safe, and easily deployable collaborative robotic systems. for manufacturing. So in Robomate project, basically we were trying to design these collaborative robot system aimed at SMEs. It basically feeds into our research on collaborative workstations where humans and robots can coexist together. And it basically explored how we can program these robots from demonstrations rather than coding them. And the last part of Live Lab 1, which is Live Lab 1C, where we evaluated the workload in these robotics environment, where we simulated an assembly station, and we were measuring the physical and cognitive demands of human during these assembly tasks. So the tools we used included ergonomic design, job rotations, and the time analysis. And results has helped us inform create or design an adaptive workstation and cobotic task allocation. Okay, yeah, so these are just highlighting some of the features of this cobot station, which is adjustable lighting, adjustable legs for ergonomics, then connect systems and touchscreens for the for measuring different physiological measures and the work area. Now I'll hand it over to Doa, who will take you over to who will give you an overview of Live Lab 2.
Yeah, thank you, Ayush, and thank you, Loredana. Life Lab 2 was focused on human performance and on automotive manufacturing. We were three early stage researchers in this Life Lab, and we work on different tasks like visual fatigue, human factor, defect detection, and failure prevention. But I will talk more about the defect detection, which I was personally involved in more than the other tasks. Ayush, if we can switch to the next slide, please. So the main purpose was to support a human operator through using AI, in particular Latin spaces, in detecting the defects in the painting process of vehicles with a low-cost solution that improved the detection while decreasing the overload on the human operator. So the idea was to move from the image space to the Latin space, because Latin space is now, I think a lot of people know that it's a very practical tool that can be reused from one field to the other. And there is a lot of work there. So it was a good idea to try it also in this use case. In order to classify the defects while also detecting the anomalies that can be presented to the human operator to be controlled or to be checked. Next slide, please, Ayush. Sorry. So we designed a framework based on 4 different phases that have 2 main goals, which are minimizing the human overhead or involvement by filtering the already known defects to be automatic labeling, while adapting dynamically to new defects that can be detected and presented to the human operator, so it will be handled manually. Also, next slide, Ayush. So we have also a SWOT analysis. There is a lot of strengths in our work, but also some weaknesses. While using AI in general has a lot of privilege because AI is advancing and improving every day. Also, it's customizable and updatable. To reduce the human workload with low-cost solution, but there's some weaknesses that the implementation in, especially in industry or manufacturing, can have a highly cost with limited training data usually, and we are now in the early development phase. And there is some potential need for manual validation still. It's not fully automatic in general. But this can open also a lot of opportunities to such solutions, because we can reach a full automation of this use case in the painting inspection process. Also, the industry leadership, transferability to other domains, and alignment with the industry 4 trends. Some threats can be also appear, like the uncertainty in the implementation, the resistance that can be also found in the industry stakeholders or partners, with the technological obstacles and the dependency on label data. So this is my part. I will give the floor to Chiara to finish the presentation. Thank you.
Thank you. It'll be a whistleblower, early presentation of some of the work that we did in Living Lab 3, which is about collaborative intelligence in control room scenario. In the next slide, we see that if you can change, the problem stem from the fact that we have noticed that the alarm overload is so-called alarm overload is basically when you consider that operator in control room have to respond to alarms, and the current standards require them to not be overloaded with more than 10 alarms per 10 minutes. And this is normally difficult to keep as a metric. As you can see in this chart, there are way more than that. So one area that we thought could be useful for collaborative intelligence is alarm filtering. So in the next slide, we saw easily clustering could respond to that situation. And even in the next slide, we said that if we want to enhance not only the reduction of the alarm, but also the information related to the alarm, so which one of them are more critical to respond to in relation to the trips that they could predict or that they could be associated to, that could also be done in an explainable AI method or fashion. In fact, we would try to use Bayesian network for this because it's a high impact area. So that according to the UI Act requires explainability. In essence, though, we try to see, okay, how could that decision support can be delivered to the operators, and how does that change their performance potentially? Because control room scenario are traditionally, they have to be very safe environments, so new technology has to be highly tested. It's a bit like aviation, so it's very difficult to make a change, especially with this type of tools. So in the next slide, we present a little bit, if you jump ahead actually twice, the next again, we try to test this hypothesis in a simulator using, it's not a digital twin because the link with the real plant was not established, but it's actually a very faithful replica of an a formaldehyde production plant. And we selected 3 scenarios with different level of complexity to test different elements of the decision support offered by the interface. So in the next slide, you could see these are the list of alarms. They're normally color-coded regarding the criticality. And we decided that for our design of experiment, we needed to look at lack of support, so the baseline, no support, paper procedure, no alarm rationalization. A second case where you have alarm rationalization and paper procedure. A third group with alarm rationalization and electronic procedure. And then a fourth group where we had alarm rationalization, screen-based electronic procedure, and an AI support agent, okay? And for us, this was a critical element in the design of experiment. In fact, in the next slide you see, we designed the interface. So the 3 screens is an ecologically valid replica of what a control room operator would find in a control room. So you have the overview screen that is demanded by the standards in the industry. Then you have 2, let's say, corollary screen where you have the detail of the mimics of the different subplants that you need to change values for, operate valves on, etc. And another screen that is dedicated to alarm trends, to information that is for decision support and alarm response normally. And in that is where on the bottom corner, right, on the suggestion area, you see we included the AI decision support system, which was based on an influence diagram mapping the behavior of the part of the plant that was in question, and was linked to a reinforcement learning algorithm that was actually suggesting the action to be taken. We found, and this is where things get a bit interesting, the next step, we looked also at metrics regarding the behavior, and we analyzed the experiment in such a way that we collected at different point in time indication about the situational awareness of the operator, where we knew, every 5 minutes, etc., what level of alarms they were facing and what they were supposed to be doing in terms of troubleshooting, etc. So that was planned very well to both collect the performance and the situational awareness. So in the next slide, you'll see that what we found and we didn't expect was that if for the first two scenario, where the level of complexity was medium-low, the people that used the advanced alarm display with the procedural AI support performed in average better than the people with no support, okay, and the people without the AI support. That changed dramatically in scenario 3. Scenario 3 is the most complex of the scenarios, and unfortunately, in that case, the performance, or if you like, the error rate, the failure rate of the people receiving the AI support was actually comparable to the one that, well, it was still lower than the people that received no support, but it was comparable to the third group that did not have AI support, and was worse than the people that had the rationalization and the paper procedure. So we had to really question ourselves why that was happening. And we think we found the key, the next slide, in the decrease situational awareness that was observed in the operator using the AI support, which meant when things are easy, even if you're not really in the loop as you're supposed to be, or your situational awareness is not optimal, you can perform well with the help of an AI agent. But if it's required, if the situational awareness is required and the situation gets complex, the use of the AI agent can induce a little bit of an out of the loop syndrome. And this is something we need to actually work on further, because we found in the next slide, we need as actually point for us to work on in the design for collaborative intelligence. And it'd be interesting to link also with Miguel about how that can relate to other form of distributed system knowledge. For us, we found that the calibration of trust and the calibration of feedback loop between the user and the AI tool was essential, or could be essential. Also, the training of the user to understand what the system can do and what the system doesn't do. For instance, it could affect the system under reliance or over reliance, because we found that that's related to also the trust or lack of trust that some of the user displayed in relation to the AI suggestion. And the functional allocation again is key in to actually have a real human in the loop. How can we allocate some function that can be automated to the automation part and keep some of the function in a real collaborative space, which means the operator still retain the situational awareness. So does it need to be given some task, even by the AI agent, to ensure that he or she is still in control of the system? So these are points. The project is near the end, but we are finding new way of continuing this work in other proposal in other projects, because it's a very interesting point moving forward. Thank you for your attention, and we're looking forward for some of the questions that you might have.
Thank you so much, Chiara. That's very interesting to see the great advancements of the AI technology, robotic technologies in domain. Some of them more broad, like what Miguel presented, and some of them apply on specific needs in the industry. I don't see any question at the moment in the chat, so I invite the participants to add them here if they have any. Otherwise, Chiara and Ayush, Doa, but also Miguel, they will be available after the webinar to answer any questions. But maybe I can start with a question that I have, and it's more or less the same question for for the both projects, let's say for both applications. Namely, where do you see the future of these technologies? Where do you think that the research that you are making right now could go in the future? What kind of other applications it could be used for in the future? So I don't know, Chiara, would you like to start?
Oh, okay. Thank you. I can start, but I like to also hear from the others and from Miguel in particular. I think the problem of transparency in high impact and human oversight and how to really play this for safety critical industry is on the forefront. We know that, for instance, in aviation, in nuclear, in control room environment, oil and gas and process industry, the industry is very cautious in introducing new software tools that can have a detrimental effect on the reliability of the overall system. And in fact, actually, though I can also explain the reliability of the latent space model in detecting defect, it's comparable to the human, but not quite as good as the human yet, okay? Which it seems surprising because we think about the human reliability as the weak link. But actually, it's not that weak because it's flexible and it adapts to situation and it's explainable at all points, even when it's sometimes unreasonable, okay? It can be. So to find the right balance between the reliability requirement, the accuracy, and the transparency, and the understanding, if really collaboration has to be put in place, there needs to be a mutual understanding of each other's limitation. There needs to be an agreement of mutual monitoring, which the humans are really, and rightly so, in my opinion, let's say, not keen on, because it means, an AI system also monitoring your state, which is something that happens in industry, like in the dead man switch on the train, but it's not as pervasive as it can be when it becomes an environment like this. They're really big open question. And we don't have answer for them, but we are moving towards answer. And we need to, because we need to understand what are the conditions for this interplay to be safe and what are the requirements we need to meet for saying that we are robust in the way of taking decision with the support of the AI and the understanding of what that gives us. So I also want to pose that question to Miguel in a way, in the sense of what their work is on the collective intelligence for this.
Yes, thank you for the question, also for the first question by Loredana and the second one from Chiara. And no, I think obviously it's a very interesting topic in general. This one about about collective intelligence, in a way also the term hybrid intelligence. It's a way related to that. So the thing is, at least from my point of view, some of the things we are working on, for example, knowledge graph, some of the technologies are there since a while now. They're like semantic web technologies. But the thing is, and one point of view could be that now that we have these powerful LLMs, for example, a lot of these ways that we use to represent knowledge that we humans use to structure knowledge will be obsolete, because we can have an AI that store the facts in whatever way she does that we don't know, it does that we don't know, and then gives us the answers, right? But the thing is that we have problems of transparency, on bias, and so one way to go is to use I mean to try to use models is a way also to guide AI, for example, or have some way that to check and to you give a reply, but also based on some facts that I know are like common knowledge in a way. Okay, that's the idea. So we are working, but it's an open research question at a bit at this point, also societal question maybe.
Chiara, if you want to
No,
complement.
I also want to listen to Ayush and Doa, but this is so topical now because our next stage on human AI collaboration is actually observing how explainability affect human decision. And there are very interesting experiments. One of the last one that has been published in Nature on this. So if you have an explainable AI suggestion, it improves the quality of the decision making. It can actually affect very positively the reliability of the human. The problem is, how can we do that in a way that doesn't de-skill the human and the oversight is true oversight, so that you retain the domain knowledge that you need to retain and not completely, let's say, lose it, because use it or lose it is a true statement in regard to human behavior. So it's a matter of finding the way of keeping the people engaged, even with tasks that are, I wouldn't say fake because it's the wrong word, but it's tasks that are there to ensure the competency and the human in the loop status of the human. If he or she is in charge of a system, they need to be verifiable in charge, and that's the issue. But there are many things where the capacity of the AI algorithm is better than the human in processing a large amount of alarms or information. We should use that. It's just a matter of, and also Ayush and Doa can explain. For Ayush, the collaboration in terms of kinesthetic teaching, having a robotic arm taking over some of the repetitive tasks. Why not? That is, it's I don't know, but the knowledge mapping, it's also very important, and it'd be interesting to see how it has been carried out, because I've seen it carried out in the safety space for accident mapping, and it needs to be, the human need to keep the oversight that the right information is being mapped in the correct way or not, the wrong links being established.
Maybe I'll pick up on what you mentioned, Chiara, and then indeed maybe ask also Ayush to maybe share some of his experience and what he thinks.
So basically, my experience is all on collaborative robots and robotics. So one thing we saw during the project was during our analysis was it's good to have human robot collaboration, but during as a supervision, where a human works as a supervisor, and where if something goes wrong during the robot task, then while robot doing some kind of task, then robot can ask for help and that kind of thing. But we saw that having a human and robot working alongside each other was creating such a huge safety risk because it's very hard to maintain the robot speed where it can be productive enough for the system. So the best way we think a human robot collaboration works is where we define in a robot task in an intuitive manner by showing the robot rather than coding the robot, by showing the robot how to do a task and then letting the robot do it on its own, and so that humans can become more of a supervisor rather than workers, so they can take over the tasks of supervising a fleet of robots rather than working alongside those robots. So that's what we have found during our work. Yeah.
That's definitely a very interesting perspective. And how about from your experience, Doa? Do you have a different perspective, maybe?
Maybe like my personal opinion that AI, as we all know, that they have succeeded in maybe two a little bit different fields, which are the control repetitive tasks, well controlled, and on the other extreme, there's also the creative and generative models that are also successful. But in between these two extremes, there's a lot of like a gray scale. that humans are already still there, like maybe sometimes they are better, maybe AI is sometimes is better. So the in-between cases, they are not clear, while explainability, like Chiara said, might try to explain why AI works in some cases, and in the same time explain why it doesn't work in other cases. So the future is still open, and there is a lot of work to understand their logic, because AI have a logic that for human so far it's not clear, and it's a little bit far from our logic. So I think there is a lot of future work to do using AI, and maybe every day has a surprise, so we can't expect what will happen in the future. So we'll see.
For sure, these technologies will evolve, and in a very brief period of time, they will be quite different to what we know them today. So with this, I think it's time for us to close the session. So I want to thank you sincerely to the speakers for your valuable insights. And of course, I want to thank the audience for their interest in the topic. I shared the links of the project in the chat. And if you want to get in touch with the speakers, they are available via LinkedIn, but also directly through the project website. I hope you found the discussions valuable and inspiring. And if you enjoyed the session, I encourage you to visit AI On Demand website to explore the assets that exist there. Maybe some of those we discussed today will also be included on the platform. And then you can also join the community of researchers to share your own resources through the platform. So you can also stay updated by following the platform on social media, on LinkedIn, X, and YouTube. So thank you once again to all of you, and I look forward to seeing you at the next sessions.
Thank you, Loredana. And share the links
Thank you
or the
so
invite
much
for the next session. We'd like to see more. Thank you.
Certainly.
For organizing this.
Thank you,
Have a nice
Loredana,
day.
and everyone.
Thank you. Bye-bye.
Bye-bye.